From the perplexing tumble of Oumuamua, we learned humility before the truly unknown, a shape unlike anything we'd imagined. Then came Borisov, a familiar comet, reminding us that the galaxy, despite its vastness, crafts worlds and wonders from the same cosmic dust as our own. And finally, the ghost of Comet Atlas, a fragile, fleeting beauty, underscored the impermanence of all things, even our own existence in a universe prone to sudden change. Scientists still ponder the true frequency of such interstellar visitors, debating how often these cosmic messengers sweep through our solar system. The next generation of observatories, from ground-based giants like Vera Rubin to space telescopes peering into the earliest moments of the universe, are poised to push back the curtains on these profound questions. They are our eyes and ears, extending our senses across unimaginable distances and through cosmic time. The universe continues to surprise us, to challenge our assumptions, and to reward our relentless curiosity. What we still don't know isn't a void to fear, but an invitation to explore, a promise of future wonders awaiting our discovery. Imagine a mission that could chase down the next interstellar traveler, rendezvous with it, and perhaps even collect samples. Such a mission would be incredibly challenging. These objects move at immense speeds, often tens of kilometers per second, relative to the Sun, and their arrival is unpredictable. Crafting a spacecraft that could launch on short notice, accelerate to comparable speeds, and then perform intricate orbital maneuvers around a tiny, fast-moving target is a monumental engineering feat, pushing the very boundaries of propulsion technology. Yet, the scientific payoff would be immeasurable, but the questions raised by Oumuamua persist, fueling a new frontier in astronomical discovery. The hunt for these interstellar messengers is about to get a significant upgrade. Enter the Vera C. Rubin Observatory, currently under construction in Chile. This isn't just another telescope. It's a revolutionary sky-scanning machine, equipped with an enormous 8.4-meter primary mirror and the world's largest digital camera, a staggering 3.2 gigapixels. It will conduct the Legacy Survey of Space and Time, or LSST. It was dark, rocky, and appeared to be tumbling end over end, perhaps shaped like a flattened cigar or even a cosmic pancake. This lack of visible outgassing, coupled with its unusual acceleration, ignited a furious academic debate. Some theories suggested it was simply a highly unusual comet, perhaps one that had lost all its volatile compounds, or whose outgassing was invisible to our instruments. Others, however, ventured into more speculative territory, proposing it might be something artificial, a light sail from an alien civilization, or even space junk from a distant star system. Imagine a silent, solitary traveler, adrift for eons, navigating the cold, dark expanse between star systems. For millennia, these interstellar wanderers were the stuff of science fiction, theoretical constructs born from our understanding of planetary formation and stellar dynamics. Then, in 2017, the universe sent us a postcard. On October 19th, the Pan-STARRS telescope in Hawaii spotted a faint, fast-moving object. It was unlike anything we had ever seen. Its trajectory clearly indicated it wasn't gravitationally bound to our sun. It was merely passing through, a fleeting ghost from another star. And Atlas, though a solar system native, dramatically illustrates the inherent volatility of icy bodies, reminding us of the dynamic and often destructive forces at play in our own cosmic neighborhood. Each object, in its unique way, pushes the boundaries of our knowledge, painting a more complete, if still largely incomplete, picture of the universe beyond our familiar skies. Its non-gravitational acceleration, without any visible outgassing, truly set it apart. It departed our solar system as mysteriously as it arrived, leaving behind a trail of unanswered questions about its true nature and origin. Atlas, conversely, was on a long-period elliptical orbit, originating from the distant Oort cloud, a vast reservoir of icy bodies surrounding our solar system. Its fate, unlike its interstellar counterparts, was not to simply leave, but to disintegrate. Its fragments continue along the original orbital path, a ghostly procession marking where a majestic comet once shone. Yet this very volatility proved its undoing. The immense forces of sublimation, coupled with the sun's tidal stresses, caused Atlas to spectacularly fragment into dozens of pieces. This event encapsulates an academic tension phrase. Scientists still debate whether such dramatic cometary fragmentation is primarily caused by internal structural weaknesses, exacerbated by outgassing, or by sudden, intense thermal stresses that literally tear the nucleus apart. The exact interplay of these forces remains a subject of ongoing research, with Atlas providing a vivid case study of a comet tearing itself to pieces under the sun's scrutiny. This similarity was both reassuring and incredibly informative, offering a baseline for what to expect from interstellar visitors. Oumuamua, however, remains stubbornly silent on this front. Despite its close approach to the sun, no cometary activity, no outgassing, no coma, no tail was ever detected. This lack of visible volatile expulsion, coupled with its observed non-gravitational acceleration, led to intense speculation. Was it made of unusually dense rock or metal? Or perhaps it possessed an exotic, invisible form of ice. Its highly elongated, cigar-like or pancake-like shape, perhaps only a few hundred meters long, was unlike anything seen before. Imagine a cosmic tumbleweed, spinning end over end, reflecting sunlight in a peculiar dance. Borisov, by contrast, presented a more conventional picture. A solid nucleus, estimated to be around 0.4 to 1 kilometer in diameter, cloaked in a developing coma, much like a typical comet from our own Oort cloud. Atlas was initially a substantial body, perhaps a few kilometers across, before its dramatic fragmentation. Having explored the individual enigmas of Oumuamua, the familiar yet foreign nature of Borisov, and the spectacular demise of Atlas, you now stand at a unique vantage point. It's time to place these celestial wanderers side by side, to truly appreciate their distinct stories and the profound lessons they offer about our universe. This comparison isn't merely about listing facts. It's about understanding the very fabric of cosmic existence. From the mundane to the truly inexplicable. Let's begin with their discovery dates, a timeline that subtly hints at our evolving observational capabilities. This academic tension phrase encapsulates the core struggle. Scientists still fiercely debate whether Oumuamua's peculiarities point to an exotic, perhaps even artificial origin, or if they are merely manifestations of natural phenomena we don't yet fully understand, pushing the boundaries of our current astrophysical models. The scientific method, by its very nature, demands extraordinary evidence for extraordinary claims. And while Loeb's hypothesis was extraordinary, the evidence, for most, remained insufficient. This idea, while captivating, immediately sparked intense debate within the scientific community. You see, the tension here is palpable. On one side, you have the cautious, methodical approach of science, demanding rigorous evidence, peer review, and a preference for the most parsimonious explanation, the simplest one that fits the data. Scientists struggled for sober explanations, meticulously analyzing every scrap of data, considering every natural possibility, no matter how exotic. For most scientists, this acceleration suggested a natural, albeit unusual, explanation. Perhaps it was a comet made of a different type of ice, like solid hydrogen or nitrogen, which would vaporize without forming a visible dust tail. Such a composition would be incredibly rare, but not impossible. However, the media, ever hungry for a compelling narrative, seized upon the mystery. Headlines screamed, speculating about alien spacecraft, advanced technology, and visitors from beyond. The public fascination with Oumuamua exploded, fueled by a deep-seated human curiosity about life beyond Earth. It was named Oumuamua, Hawaiian for scout or messenger from afar, and it quickly became the subject of unprecedented scientific scrutiny and, perhaps more famously, global media frenzy. What made Oumuamua so extraordinary was its trajectory. Unlike any comet or asteroid we had ever seen, its path clearly indicated it was not gravitationally bound to our sun. This was our first confirmed interstellar visitor, a true traveler from another star system, passing through our cosmic neighborhood before continuing its lonely voyage into the vast unknown. They are the silent witnesses to the cosmic ballet, helping us understand the intricate dance of our solar system, one fleeting visitor at a time. This convergence of ground-based surveys, amateur dedication, and space-based assets represents a profound shift. Modern sky survey technology has truly transformed our ability to catch brief cosmic visitors in real time. We are no longer simply reacting. We are proactively searching, mapping, and predicting. The sheer volume of data generated by these surveys, however, poses its own challenges, leading to ongoing discussions about the most effective algorithms for real-time threat assessment versus long-term orbital prediction. When a new object is detected by a survey like Pan-STARRS or Atlas, the initial data might be sparse. It's often these passionate amateur astronomers, with their agility and dedication, who provide crucial follow-up observations, helping to refine orbits, confirm discoveries, and even find objects missed by the larger automated systems. They form a global network of citizen scientists, proving that the spirit of discovery thrives beyond institutional walls, a testament to humanity's innate curiosity. Beyond Earth's atmosphere, space-based telescopes offer another vital perspective. Complementing Pan-STARRS is the Asteroid Terrestrial Impact Last Alert System, or ATLAS. With telescopes strategically located across the globe, in Hawaii, Chile, and South Africa, ATLAS provides an even more rapid, wide-field scan. Its mission is explicit: to detect smaller asteroids days or even weeks before a potential Earth impact. While Pan-STARRS might find objects years out, ATLAS is the system designed to give us that critical last alert, identifying objects that could pose an immediate, albeit localized, threat. Discoveries were often serendipitous, requiring patient, long-exposure photography or the keen eye of an individual astronomer. Today, you stand on the precipice of a new era, one where automated systems act as our planetary watchdogs, ceaselessly scanning the heavens. At the forefront of this revolution are groundbreaking facilities like Pan-STARRS and ATLAS, perched atop Haleakala, a dormant volcano on Maui, Hawaii, lies the Panoramic Survey Telescope and Rapid Response System, or Pan-STARRS. This isn't just one telescope. It's a network designed for a singular, ambitious purpose: to map the entire observable sky multiple times a month. The precise mechanism behind Oumuamua's final, mysterious nudge remains one of its most compelling, unresolved questions, pushing the boundaries of our imagination and our understanding of interstellar visitors. The universe, it seems, has a profound way of surprising us, presenting phenomena that challenge our neat categories and force us to imagine possibilities beyond our current frameworks. You can picture sunlight, a relentless stream of tiny energy packets, gently pushing against a vast, reflective surface. This light pressure, or radiation pressure, is a known physical phenomenon, fundamental to concepts like solar sails. If Oumuamua were indeed a natural object with such an extreme geometry, perhaps a fragment of a tidally disrupted planet, then light pressure could provide that persistent, non-gravitational nudge without any need for outgassing. This radical, highly speculative idea, requiring an object of unprecedented natural form, offers an elegant explanation for the complete absence of any detected gas or dust. However, the very existence of such large, stable bodies of exotic ices in interstellar space raises profound questions about their formation and survival. Could such a fragile object survive for millions of years without evaporating? Scientists are actively modeling these scenarios. Yet the puzzle deepens. Some theories suggest even exotic ices might not fully account for the acceleration, or their presence in such quantities is simply too difficult to explain given interstellar travel's harsh realities. This pushes speculation further, leading to visionary, almost science fiction-like possibilities. If it wasn't water ice, what else could provide such a mysterious push? One compelling, though highly unusual hypothesis suggests Oumuamua might have been composed of exotic ices, like solid hydrogen or nitrogen. Imagine a chunk of frozen hydrogen or nitrogen, substances that sublimate at incredibly low temperatures. As Oumuamua approached the sun, Even weak solar radiation could have caused these exotic ices to sublimate rapidly, creating a gentle, persistent thrust. The elegance of this idea lies in its ability to explain the observational conundrum. These escaping gases, often carrying fine dust particles, form a glowing coma and a spectacular tail, acting like tiny rocket thrusters that subtly alter the comet's path. This well-understood phenomenon provides a clear, physical mechanism for a non-gravitational push. However, here is where Oumuamua truly defied all expectations and plunged scientists into a profound mystery. Despite intense scrutiny from the most powerful telescopes on Earth and in space, instruments like Hubble and Pan-STARRS, not a single trace of gas or dust was detected. As Oumuamua made its closest approach to our Sun, its initial trajectory seemed straightforward. But as it began its long journey back into the interstellar void, something truly extraordinary and deeply puzzling began to unfold. You watch the orbital data, meticulously collected by telescopes across the globe, and a subtle yet undeniable anomaly emerges. Oumuamua isn't just following the sun's gravitational pull. It's being gently but persistently nudged. It's accelerating, as if an invisible hand is pushing it from behind, adding the mysterious boost to its departure velocity. Borisov, a pristine icy time capsule, confirms that comet-like processes are indeed universal. Atlas, a fragile icy structure, showcases the destructive forces at play. Scientists still grapple with the precise nature of Oumuamua's surface, debating whether its unusual reflectivity points to a truly bare metallic core, a rocky composition, or perhaps a thick, protective crust of complex organic molecules baked by eons of interstellar radiation. An exotic mix indeed. This academic tension highlights the frontier of our knowledge, where new data continually refines our understanding. It was a cosmic ice chest, delivering samples of primordial interstellar ices directly to our telescopic gaze. And then there was Atlas, the comet that dramatically fell apart before our very eyes. Its spectacular disintegration, as we touched upon earlier, was a direct consequence of its fragile, icy composition. Its rapid brightening and subsequent fragmentation into dozens of pieces confirmed it was a loosely bound aggregate of dust and ice, unable to withstand the stresses of solar heating and tidal forces. It presented a stark contrast to what many expected from a typical comet-like object formed in the frigid outer reaches of another star system. The idea of a dense, possibly metallic, interstellar object was and remains a truly exotic prospect, hinting at formation processes that might differ significantly from our familiar icy comets. Then came Borisov, a visitor that couldn't have been more different. Unlike Oumuamua's barren exterior, Borisov proudly displayed a glorious, active coma and a distinct tail as it approached the sun. As we've tracked their incredible journeys and pondered their mysterious origins, a fundamental question emerges. What are these interstellar wayfarers actually made of? You might imagine them as simple chunks of rock or ice, but the reality, as astronomers have discovered, is far more intricate and revealing. Each visitor, in its unique composition, paints a stroke on the canvas of cosmic chemistry, offering tantalizing clues about the diverse building blocks scattered across the galaxy. Take Oumuamua, for instance. Its enigmatic nature, which we've discussed in terms of its acceleration, extends deeply into its material makeup. The key scientific fact is that the vast majority of potential impactors are either too small to survive atmospheric entry or are on orbits that simply do not intersect with our planet. The universe is incredibly vast, and empty space is, by its very definition, mostly empty. However, this statistical reassurance doesn't entirely erase humanity's underlying vulnerability. The thought experiment reminds us that while the odds are overwhelmingly in our favor, the consequences of a major impact would be catastrophic, a stark reminder of our delicate existence on this pale blue dot. It's a quirky thought. You are in fact being peppered by space debris right now, but it's too small to notice. The academic tension here lies in the long-term prediction for truly uncharted objects. While we have excellent models for known solar system bodies, predicting the exact trajectory of a newly discovered, fast-moving comet from the Oort cloud or an interstellar object that appears suddenly presents a different challenge. Scientists still debate the completeness of our detection capabilities for these truly surprise visitors. For these known entities, their trajectories are meticulously calculated, often decades and even centuries into the future. The vast majority pose no threat whatsoever. But what about the truly unexpected? The rogue object from the Oort cloud, or even further afield, an object whose path we haven't yet charted. This is where the sheer immensity of space becomes our greatest shield. Picture Earth as a tiny target, a speck in a shooting gallery spanning light years. The odds of a direct hit, especially from an object large enough to cause global devastation, are astronomically small. As we've journeyed through the cosmic ocean, charting the incredible diversity of objects that traverse our solar system and beyond, a fundamental question invariably arises, one that sparks both wonder and a primal unease. Could any of these celestial wanderers truly hit Earth? It's a thought experiment that brings the vastness of space uncomfortably close, forcing us to confront our place in a dynamic, sometimes chaotic universe. Let's confront this question head-on, not with fear, but with the cold, hard clarity of numbers. These hyperbolic highways are, in essence, the galaxy's connective tissue, allowing matter, energy, and perhaps even the complex organic building blocks of life to travel between star systems. Every time a star forms or a planetary system settles into its stable configuration, there's a significant chance some material gets flung out into the interstellar medium, becoming a potential future interstellar visitor. Our solar system isn't just a destination for these travelers. It's a cosmic waypoint, a gravitational crossroads where objects from distant suns briefly intersect with our own before continuing their endless journey. This brings us to an academic tension phrase that continues to fuel intense scientific debate and exploration. Scientists still debate whether Oumuamua's peculiar acceleration, its lack of a visible tail, and its unusual shape hint at a truly novel class of interstellar object, perhaps even a fragment of a planet that never fully formed, ejected during a violent early epoch of another star system. Some theories propose it could be a hydrogen iceberg, or even a nitrogen iceberg, explaining the lack of a visible tail, an object ejected from its home star system, perhaps by a close encounter with a massive gas giant, or flung out during the chaotic birth of a star cluster, gains enough speed to escape its parent star's gravitational dominion. It then embarks on an epic, solitary journey through the vast emptiness of interstellar space, a voyage that can span millions or even billions of years. Instead, its highly variable brightness suggested an extremely elongated cigar-like or pancake-like shape, tumbling end over end as it traveled through space. This was unlike anything we had ever seen, and stranger still, as it departed our solar system, it exhibited a slight non-gravitational acceleration, hinting at outgassing, a common characteristic of comets. Yet despite this, no visible coma or tail was ever detected, leading to intense speculation. Was it a peculiar, dry comet with hidden volatiles, or something far more exotic? Scientists meticulously tracked its journey, observing it approach our sun from above the ecliptic plane, slingshot around it at a blistering speed of nearly 88 kilometers per second, and then accelerate away, destined never to return to our solar system. Its trajectory was a textbook hyperbola, a clear signature of its extrasolar origin. Just 2 years later, in 2019, comet Borisov followed, another unmistakable interstellar visitor. Unlike a planet, which falls into a repetitive, closed loop around its star, or even a long-period comet, whose elongated orbit still eventually brings it back, these interlopers possess a velocity so immense, so exhilarating, that our sun's mighty gravity can only bend their path, never truly capture them. This is the key scientific fact at the heart of their journey. An object on a hyperbolic trajectory has more than enough kinetic energy to overcome the gravitational pull of the body it's passing, meaning its speed exceeds what we call its escape velocity. It allowed researchers to refine their complex models of cometary evolution and destruction, pushing the boundaries of our understanding of these enigmatic wanderers and the violent lives they lead. It was a powerful reminder that even in the seemingly predictable dance of celestial mechanics, there are always elements of surprise, and sometimes a comet's greatest show is its final, spectacular collapse, a poignant farewell to the cosmic stage. What specific internal structure, what exact composition, perhaps a particularly porous nucleus or one with hidden fault lines, or what particular rotational stress makes one comet succumb while another, seemingly similar, survives its perihelion passage intact, emerging on the other side as a renewed, if slightly smaller, object. Was Atlas's nucleus particularly weak? Perhaps a very young comet making its first fiery dive into the inner solar system after eons in the frigid, undisturbed Oort cloud, making it more susceptible to fragmentation due to its pristine, volatile-rich interiors. This sudden demise, captured in stunning detail by instruments like the Hubble Space Telescope, which provided breathtaking close-ups of the spreading fragments, offered a stark, undeniable illustration of the profound fragility of these icy visitors. One moment, Atlas was a harbinger of potential wonder, promising a grand show. The next, it was a scattered collection of cosmic debris, its grand performance canceled indefinitely. It showed us, with brutal clarity, how easily these cosmic travelers can vanish before our eyes, their existence fleeting, their fate often sealed by the very forces that might otherwise make them spectacular. Picture steam vents on an alien world, magnified to a scale that tears apart a mountain-sized object. Simultaneously, the sun's powerful gravitational pull exerted immense tidal forces upon the comet. To understand this, imagine the difference in gravitational attraction between the comet's sun-facing and far sides. The sun pulls on the near side with slightly more force than on the far side. This differential pull, though seemingly minuscule on human scales, becomes incredibly significant for a loosely bound object like a comet. Imagine, if you will, watching a magnificent ice sculpture, meticulously crafted and full of potential, suddenly crack and splinter into countless shards under an invisible, immense pressure, its form irrevocably lost. That's precisely what happened to Atlas, but on a cosmic scale. Its fragile body, a loosely bound aggregate of ice, dust, and rock, simply could not withstand the intensifying stresses of its journey, proving too harsh for its delicate constitution. The primary culprits were the relentless, escalating forces of our own star. Its trajectory suggested a remarkably close pass by the sun, a perihelion that, under ideal circumstances, could supercharge its tail and make it an unforgettable sight for millions across the globe. The data flowing in from observatories around the globe painted a picture of a rapidly brightening object, its coma expanding dramatically, its tail beginning to stretch across the void like a cosmic feather. It felt like we were on the cusp of a truly historic event, a rare opportunity to witness a grand celestial ballet unfold right before our eyes, a once-in-a-lifetime spectacle. It was a tragic end for what could have been a once-in-a-lifetime celestial event. But in its demise, Atlas offered us invaluable insights into the life and death of comets, revealing the intricate dance of forces that shape these beautiful, ephemeral visitors. Scientists still debate the precise mechanisms that trigger such dramatic fragmentation events in comets, especially those far from the sun, weighing factors like rotational stress, thermal shock, and the volatile composition of their nuclei. Some theories suggest that pockets of highly volatile ice deep within the nucleus could suddenly sublimate, creating explosive jets that tear the comet apart from within. Others point to the comet's history, suggesting that previous close encounters with the sun or gravitational tugs from planets could have weakened its structure over millennia, making it susceptible to collapse during its next inbound journey. As they approach the sun, the increasing solar radiation causes the ice to sublimate, turn directly from solid to gas, releasing dust and gas, forming the coma and tail. But sometimes, this process, combined with other stresses, can be too much. The rapid rotation of the nucleus, the differential heating across its surface, or even internal gas pressure can create fissures and cracks, eventually leading to a catastrophic breakup. It's a cosmic dance of creation and destruction, where the very forces that make a comet spectacular can also tear it asunder. It was as if Atlas was awakening, shaking off eons of frozen slumber in the Oort cloud, responding to the sun's gentle yet relentless embrace. Its journey inward was accelerating, promising a grand display as it neared perihelion, its closest approach to our star. But the universe, as always, holds its own surprises. Just as hopes reached their zenith, a different, more somber story began to unfold. In March and April of 2020, observations started to reveal something unexpected, something dramatic. The comet's nucleus, that icy heart, wasn't merely brightening. It was breaking apart. You stand on the precipice of discovery, witnessing the early reports ripple through the astronomical community. Discovered by the Asteroid Terrestrial Impact Last Alert System, an ironic name perhaps for a system primarily designed to detect asteroids that might pose a threat to Earth. Comet Atlas began to capture attention for an extraordinary reason. It brightened rapidly, far more quickly than typical comets. This sudden surge in luminosity wasn't just a minor curiosity. It ignited a fervent hope, a collective whisper among skywatchers. Could this be the next great comet? The subtle nuances, if and when they are precisely measured and understood, could hold vital clues to the specific conditions of Borisov's distant home system, offering an unprecedented window into another star's primordial past and refining our models of planet formation beyond our solar system. Ultimately, this interstellar visitor, so outwardly normal in its composition and behavior, became a powerful testament to the shared chemistry of the cosmos, while simultaneously opening new avenues for understanding the subtle diversities that might exist in the vast, star-strewn ocean of our galaxy. Water in Earth's oceans has a particular DH ratio, and comets from the outer solar system often have higher ratios, indicating formation in colder regions. If Borisov's DH ratio were significantly different, it would imply a very distinct formation environment in its home system. Astonishing, because it offered tangible, irrefutable proof that other star systems are perfectly capable of producing icy wanderers much like ours, loaded with the very raw materials that seeded our own planet and perhaps eventually life itself. It expanded our understanding of the cosmic commonalities that bind the universe together, painting a vivid picture of a galaxy teeming with familiar, if distant, worlds, each with its own story, yet all sharing a common chemical heritage. Yet, even with these striking similarities, some academic tensions persist, keeping the scientific community engaged in lively and crucial debate. This was the very same chemical cocktail, the very same primordial brew, the identical suite of building blocks found in the comets born and raised right here in our solar system's own backyard. Those icy time capsules preserving the pristine conditions of our sun's formation. Believed to have delivered water and organics to early Earth, this made Borisov both profoundly comforting and utterly astonishing, a duality that captivated researchers. Comforting, because it suggested a universal recipe for these celestial time capsules, a common cosmic chemistry that transcends individual star systems. These powerful tools don't just capture an image, they perform a cosmic autopsy, dissecting the light emitted or reflected by an object into its constituent wavelengths, much like a prism splits white light into a vibrant rainbow. Every element and molecule in the universe leaves a unique fingerprint of absorption or emission lines in this spectrum, a distinct barcode that reveals its identity. And Borisov's fingerprints were unmistakable. Echoing across the vastness of space. From this expanding cloud, the relentless pressure of solar radiation and the solar wind pushed streams of gas and dust away, creating two distinct, magnificent, sweeping tails that stretched for millions of kilometers. One, a broad, diffuse dust tail, curved gently away from the sun, while the other, a straighter, often bluer ion tail, pointed directly opposite the sun, driven by the solar wind's magnetic fields. As we saw earlier, the very existence of an interstellar object like Borisov was a groundbreaking discovery, a true cosmic anomaly that challenged our understanding of the universe's wanderers. It was a messenger from another star, a ghost in our cosmic machine, hurtling through the void. Yet as this enigmatic traveler drew closer to our sun, the most astonishing revelation wasn't its alien origin, but its profound familiarity. Under the sun's increasing warmth, Borisov began to awaken from its deep interstellar slumber. The debate continues to fuel our quest to understand the true prevalence and nature of interstellar wanderers, pushing the boundaries of our cosmic census. The arrival of 2I Borisov provided an invaluable, albeit fleeting, opportunity. Astronomers around the world turned their most powerful telescopes towards it, collecting a wealth of data as it made its swift pass through the inner solar system. They studied its size, its rotation period, its precise chemical makeup, even the dust grains within its tail, all to piece together the story of its distant home. This suggested that the chemical processes forming icy bodies, and perhaps even planets, might be remarkably consistent across the galaxy. Yet, this very familiarity sparks a profound academic tension. Does 2I Borisov suggest that the formation of planetary systems and the icy debris they eject follows a universal template, implying that exoplanetary systems might be far more like our own than we previously imagined? Or is Borisov merely an outlier, a lucky catch whose composition just happens to mirror our own, while the true diversity of interstellar objects remains largely hidden, perhaps dominated by the more exotic forms like Oumuamua? The volatile compounds within, water ice, carbon monoxide, hydrogen cyanide, and others, began to sublimate, turning directly from solid to gas. This process created a distinct glowing coma, a hazy atmosphere of gas and dust surrounding the nucleus, and a magnificent tail stretching millions of miles into space, pushed away by the solar wind and radiation pressure. This was the classic image of a comet, just like Halley's or Hale-Bopp, but originating from light years away. This normal behavior was, in its own way, just as astonishing as Oumuamua's strangeness. What Borisov didn't immediately know, but what professional astronomers quickly confirmed, was that this was no ordinary comet. Within days, follow-up observations from telescopes around the world, like the Gemini North Telescope in Hawaii and the European Southern Observatory's Very Large Telescope in Chile, precisely charted its trajectory. Its path was unmistakably hyperbolic, meaning it was moving too fast to be gravitationally bound to our sun. This was 2I Borisov, and like Oumuamua before it, its origin was unequivocally interstellar. As we explored the enigmatic Oumuamua, a silent, tumbling mystery from the void, you might have been left with a sense that all interstellar visitors would be so utterly alien, so unlike anything we've ever encountered. You might have wondered if the universe beyond our solar system held only the bizarre and the inexplicable. But just 2 years later, the cosmos offered a different kind of greeting, one that felt surprisingly familiar, yet no less profound in its implications. Imagine a clear August night in 2019, far from the multi-million-dollar domes of professional observatories. Some theories suggest its peculiar erratic spin might be influenced by outgassing too faint for our telescopes to detect, or by an internal structure causing it to tumble uniquely, failing to find a stable axis due to its extreme dimensions. Others argue that its extreme shape is a direct consequence of its origin, perhaps formed by a tidal disruption event around a star, where gravitational forces stretched and molded it into its bizarre form before flinging it into interstellar space. This unprecedented combination of an extreme erratic shape, a complete absence of cometary activity, and an ancient, weathered surface left the scientific community reeling. For centuries, astronomers have meticulously categorized small celestial bodies into well-defined classes: the rocky asteroids, the icy comets, the distant dwarf planets. But Oumuamua refused to fit into any neat boxes. It had no tail, so it wasn't a comet. It was too elongated, too fast, and too unique in its spin to be a typical asteroid. This puzzling, defiant lack of a cometary coma was a major point of contention, challenging the very definition of an interstellar visitor. Was it truly devoid of ice, or was its ice somehow buried deep beneath an insulating crust, preventing outgassing? The absence of a coma meant its observed non-gravitational acceleration couldn't be explained by typical cometary outgassing, adding another layer of weird physics. Its surface, too, held crucial clues and raised even more questions. Picture it, a sliver of rock, drifting through the vacuum like an impossibly thin shard of obsidian or a flattened ancient coin, constantly flipping and turning. This extreme geometry, whether it was the needle or the pancake, represented a primary puzzle. Such an elongated or flattened shape is inherently unstable, requiring immense material strength to hold together under its own rotation, let alone interstellar stresses. It was a form that seemed too fragile, too improbable, to survive eons of cosmic travel without breaking apart. But the oddities didn't stop at its bizarre form and chaotic spin. Instead, its brightness changed by a staggering factor of 10 or more over just a few hours, repeating this dramatic fluctuation. This extreme variability signaled an object that wasn't merely rotating along a single axis, but tumbling wildly, erratically, end over end, spinning along multiple axes in a chaotic, unpredictable pirouette. This chaotic rotation was a significant puzzle. Most small celestial bodies, over eons, shed excess energy to settle into stable, predictable rotations. Oumuamua's persistent, erratic spin suggested something highly unusual about its formation, its internal structure, or perhaps even its violent journey through interstellar space. This realization has spurred new initiatives, new search strategies, and new instruments designed specifically to catch the next messenger from afar, hoping to gather even more data and perhaps solve some of the enduring mysteries that Oumuamua left in its wake. We are now actively scanning the skies, not just for objects within our system, but for the silent travelers that bridge the immense voids between stars, eager for the next encounter that might further illuminate the universe's grand narrative. It confirms that star systems actively eject material into interstellar space, material that can then travel vast distances and potentially seed other star systems. This object, perhaps a fragment from a shattered planet or a leftover from a stellar formation event in a distant solar system, carried with it clues about the processes of planetary formation far beyond our cosmic home. Its journey across light years of emptiness to briefly grace our solar system is a testament to the dynamic and interconnected nature of the galaxy. It wasn't just coasting. Something was subtly pushing it. Typically, such acceleration in comets is attributed to outgassing, the expulsion of ice and dust as they warm near the sun. Yet Oumuamua showed no visible signs of a coma or tail, the telltale indicators of cometary activity. This absence of a visible tail, combined with its unusual shape and trajectory, fueled intense academic tension and debate. Scientists still grapple with the exact nature of this acceleration. Was it a peculiar form of outgassing, perhaps from volatile ices hidden beneath the crust, or something else entirely? The name itself, chosen by its discoverers, is Hawaiian for a messenger from afar arriving first, a poetic and apt description for this cosmic trailblazer. Its arrival marked not just a scientific discovery, but the beginning of a brand new chapter in astronomy, a profound shift in perspective that opened our eyes to the potential for material exchange across the galaxy. For centuries, we had speculated about such visitors, but now one had undeniably arrived, presenting itself for our fleeting observation. The discovery sent ripples of excitement. Our journey through the cosmos has shown us the wonders within our own solar system. But what lies beyond? What messengers might the vast emptiness between stars send our way? You stand now in October 2017, a pivotal moment when the universe decided to send us a truly extraordinary visitor. one that would redefine our understanding of our place in the galactic neighborhood. Imagine the quiet hum of the Pan-STARRS telescope in Hawaii, diligently scanning the night sky. On October 19, 2017, its automated systems flagged a faint, fast-moving speck of light. So when we speak of falling objects, we must now distinguish between the ephemeral, self-contained fireworks of our own solar system, the meteors, and the truly alien, interstellar messengers like Oumuamua and Borisov. The former are a constant, comforting reminder of our cosmic dust cloud, orbiting our home star for billions of years. The latter are rare, enigmatic envoys from the universe beyond, tarrying secrets from distant stars and hinting at the vast, unexplored wonders of the galaxy. Oumuamua, in particular, presented a fascinating puzzle. Beyond its unusual, highly elongated or flattened shape, it exhibited a slight, inexplicable, non-gravitational acceleration as it sped away from the sun, as if something was subtly pushing it. This behavior is typical of comets' outgassing, but Oumuamua showed no visible tail or coma, defying easy explanation. Scientists still debate whether this acceleration was due to the outgassing of exotic, supervolatile ices, too faint to detect, or perhaps some other unknown natural phenomenon, like solar radiation pressure, acting on an unusually thin, flat object. Scientists still debate whether this acceleration was due to the outgassing of exotic, supervolatile Oumuamua, was estimated to be hundreds of meters long, an elongated, cigar-like shape, or perhaps a flat pancake, depending on the viewing angle, far larger and more substantial than any typical dust grain meteor. Borisov, on the other hand, was a comet several kilometers in diameter, complete with a tail of gas and gust, a truly massive object by comparison to our everyday shooting stars. Their trajectories are the definitive giveaway. Instead of orbiting the sun, like everything else in our solar system, they follow distinct hyperbolic paths. This means they approach our sun with such high velocity that its gravity isn't strong enough to capture them into an orbit. Instead, they slingshot around our star and then depart, accelerating back into interstellar space, never to return. This distinct, open-ended trajectory is the unmistakable signature of an object originating from outside our gravitational sphere of influence, a cosmic fingerprint of its extrasolar birth. The scientific community was and remains captivated by these interstellar interlopers. Just 2 years later, in 2019, comet Borisov followed, unequivocally proving that our local cosmic neighborhood is not entirely self-contained, but rather a thoroughfare for wanderers from other star systems. These aren't just larger versions of meteors. They are fundamentally different. While a meteor is a tiny piece of our solar system, briefly lighting up our atmosphere, Oumuamua and Borisov are true galactic nomads, ejected from their home star systems, perhaps millions or even billions of years ago, traversing the vast emptiness between stars for eons before serendipitously encountering our sun's gravitational pull. Indeed, billions of these tiny particles enter our atmosphere every single day, most burning up completely long before they ever reach the ground. A constant, fiery rain of solar system dust. Only the largest, most resilient pieces survive this fiery descent to become meteorites, providing scientists with tangible samples of extraterrestrial material. These are the familiar falling objects, predictable, numerous, and entirely homegrown within our solar system. These aren't stars at all, of course. Instead, they are typically tiny dust grains, often no larger than a grain of sand or a small pebble, shed by comets or asteroids as they orbit our sun. These celestial crumbs are essentially the leftover building blocks from our own solar system's formation, continuously orbiting until they eventually cross Earth's orbital path. As our planet sweeps through these trails of cosmic detritus, these minuscule particles slam into our atmosphere at incredible speeds, typically ranging from 11 to 72 kilometers per second, or about 25,000 to 160,000 miles per hour. What do these alien rocks and icy travelers tell us about our place in the galaxy and the universe beyond? Join us as we unravel the stories these celestial strangers bring. Let's dive in and explore how it all unfolds. Yet, these three encounters have expanded our sense of belonging, weaving us into a larger, dynamic cosmic community. We are left not just with knowledge, but with an open invitation, waiting for the next whisper from beyond the stars. And perhaps, in understanding the patterns of our planet and our universe, we begin to understand ourselves. And with each new observation, each new theoretical leap, we edge closer to understanding the grand, intricate dance of existence itself. Direct observation, close-up imaging, and spectrographic analysis could finally answer questions about their composition, their origin, and whether they truly harbor any unusual or even artificial characteristics. It would be humanity's first direct contact with matter from another star system, a tangible piece of a distant cosmic story. The mysteries surrounding interstellar visitors are just one facet of the vast unknown that still beckons. From the enigmatic nature of dark matter and dark energy, which sculpt the very fabric of the universe, to the precise conditions that spark life on other worlds, our journey of discovery is far from over. Every few nights, the Vera Rubin telescope will survey the entire visible southern sky, creating a vast, dynamic movie of the cosmos. Its wide field of view and rapid cadence are specifically designed to detect transient events, supernovae, asteroid close passes, and crucially, faint, fast-moving objects like interstellar visitors. Scientists anticipate that the Vera Rubin will discover dozens, perhaps even hundreds, of new interstellar objects over its 10-year operational lifespan, transforming our understanding of their prevalence and characteristics. But merely finding them is just the first step. The ultimate dream for many scientists is to intercept one. The truth, for now, remains shrouded in mystery, a testament to the universe's capacity for surprise. Oumuamua's brief visit, lasting only a few weeks before it sped away into the black, opened our eyes to a new class of celestial objects. If one interstellar visitor passed through our system, how many more are out there? How common are they? What secrets do they carry from their distant homes? Just 2 years later, in 2019, we found another. 2I Borisov. A much more conventional comet, complete with a fuzzy tail, unequivocally confirming the existence of these cosmic drifters. This was Oumuamua, the first confirmed interstellar object, a name meaning scout or messenger from afar in Hawaiian, perfectly capturing its enigmatic arrival. But Oumuamua wasn't just a curiosity. It was a cosmic riddle wrapped in an enigma. As scientists meticulously tracked its path, they noticed something peculiar. It was subtly accelerating, deviating from the trajectory predicted solely by our sun's gravity. This non-gravitational acceleration is typical for comets, as ice sublimates and releases gas, creating a tiny jet propulsion. However, Oumuamua showed no signs of a cometary tail or outgassing. As we've journeyed through the cosmic tapestry, piecing together the grand narrative of stars, galaxies, and the potential for life, it's easy to feel a sense of profound understanding. Yet the universe, in its infinite wisdom, always holds a few wild cards, reminding us that our knowledge, however vast, is merely a glimmer in the darkness. You stand now at the edge of the known, gazing into the profound abyss of what we still don't comprehend. And perhaps this side-by-side comparison highlights why Oumuamua remains so profoundly mysterious, a true enigma that challenges our understanding of interstellar objects. It didn't fit the cometary mold, nor the asteroid mold, forcing us to consider entirely new categories of celestial wanderers. Borisov, on the other hand, perfectly fit the cometary mold, providing a crucial control group for what a typical interstellar comet looks like, confirming our expectations and expanding our cosmic census. Now, let's trace their orbits and fates. Both Oumuamua and Borisov shared the defining characteristic of a hyperbolic orbit, meaning they entered our solar system from interstellar space, made a single pass, and are now hurtling back out, never to return. Borisov's trajectory was consistent with its observed outgassing, its slight acceleration perfectly explained by the rocket-like effect of escaping gases. It was a textbook interstellar comet, a cosmic messenger from another star, now continuing its lonely journey across the galaxy. Oumuamua's orbit, however, was the source of much head-scratching. Here lies a quirky detail. One theory, quickly dismissed by most, even pondered if the acceleration could be due to solar radiation pressure acting on an extremely thin, light object akin to a light sail, a notion that fired the imagination but lacked robust evidence. The absence of a tail for Oumuamua, yet its clear acceleration, remains a profound puzzle. Atlas, our solar system's own dramatic performer, showed us the spectacular, and often violent, side of cometary composition. Rich in highly volatile ices, it began to sublimate furiously as it neared the sun, creating a magnificent, rapidly expanding coma. Its initial size promised a grand spectacle, a testament to the raw material still locked away in our solar system's icy fringes. Their compositions and behaviors are where the true mysteries begin to unravel or deepen. Borisov, the quintessential interstellar comet, displayed all the classic signs: a bright coma of gas and dust, a distinct tail, and spectral signatures confirming the presence of water ice, carbon monoxide, and other volatiles. It was, in essence, a cosmic twin to our own comets, providing a key scientific fact, definitive proof that other star systems form and eject comets composed of familiar materials. Oumuamua burst onto the scene in October 2017, a startling first. Then, in August 2019, came Borisov, confirming that Oumuamua wasn't a singular anomaly. Comet Atlas, while a solar system native, truly captured public attention in early 2020, as it brightened dramatically, offering a stark contrast to its interstellar cousins. This sequence of observations underscores a rapidly advancing astronomical vigilance, allowing us to catch these fleeting visitors with increasing precision. Next, consider their sizes and shapes, a visual testament to their origins and journeys. Oumuamua, as we've discussed, defied expectations. It served as a stark reminder of the delicate balance between open-minded speculation, which is vital for scientific progress, and the strict adherence to verifiable data, which prevents science from devolving into mere fantasy. Oumuamua continues its journey, a silent, enigmatic witness to humanity's ongoing struggle to reconcile wonder with proof, and to navigate the complex interplay between cautious science and the irresistible pull of the unknown. They pointed out that while the hydrogen iceberg theory or the nitrogen iceberg theory were unusual, they still fit within known physics and chemistry, even if we hadn't observed such objects before. On the other side, you have the powerful allure of cultural narratives, shaping public imagination and amplifying sensational claims. The idea of an alien artifact taps into a primal human desire to not be alone, a narrative far more compelling to many than a chunk of exotic ice. Amidst this burgeoning media hype, a prominent voice emerged from the academic world, Harvard astronomer Avi Loeb. He proposed a highly controversial yet undeniably intriguing hypothesis. Given Oumuamua's unusual acceleration and its initial, albeit later revised, elongated shape, Loeb suggested it might not be a natural object at all. Instead, he theorized it could be an artificial construct, perhaps a light sail, a thin, wide object designed to be propelled by the pressure of starlight, or even a piece of alien technology, a probe sent by an extraterrestrial civilization. Initially, scientists categorized it as a comet, then an asteroid, as it lacked the telltale coma of gas and dust that typically surrounds icy comets when they approach the sun. But then came another baffling observation. Oumuamua was subtly accelerating, as if something was gently pushing it. Yet still, no visible outgassing could explain this non-gravitational boost. This is where the story truly diverges. As we've journeyed through the cosmos, understanding the forces that shape galaxies and the very fabric of space-time, you might assume our understanding of celestial mechanics is relatively complete. But sometimes, the universe throws us a curveball. A visitor so unexpected, it challenges our very definitions and ignites the public imagination in ways scientists rarely anticipate. This is precisely what happened in October 2017. When the Pan-STARRS telescope in Hawaii spotted a faint, fast-moving object hurtling through our solar system. Scientists still debate the optimal balance of resources. Should we prioritize building more wide-field ground surveys or invest in more advanced space-based observatories for even earlier detection and characterization? Regardless of the ongoing discussions, the impact is undeniable. The night sky, once a realm of mystery and sudden, unexpected events, is slowly yielding its secrets to our persistent gaze. The telescopes, whether massive instruments on remote peaks, robotic sentinels, or the focused lenses of dedicated amateurs, are our collective eyes, ever watchful, ever learning. Missions like NEOWISE, a repurposed infrared telescope, have tirelessly scanned the skies for asteroids and comets, particularly those that are dark and difficult to spot in visible light. By observing in infrared, NEOWISE can detect the heat signature of these objects, revealing those that might otherwise remain hidden. While not designed for rapid, wide-field discovery in the same way as ground-based surveys, space telescopes offer unparalleled clarity and the ability to observe in wavelengths blocked by our atmosphere, providing detailed characterization of objects once they are found. These robotic eyes work autonomously, scanning the entire observable sky several times every clear night. A relentless vigil against the unexpected. The data pours in, processed almost instantaneously, turning what used to be a theoretical risk into a quantifiable, monitored reality. Yet, the story of cosmic discovery isn't solely written by colossal, government-funded observatories. Here's a quirky, inspiring detail: the invaluable contributions of amateur astronomers. Many dedicated individuals, often operating from their backyards or private observatories, possess equipment rivaling professional setups of just a few decades ago. Its powerful digital cameras capture vast swathes of the night, generating petabytes of data. Scientists then employ sophisticated algorithms to compare images taken on different nights. When an object shifts its position against the static backdrop of stars, it flags a potential moving target, an asteroid, a comet, or perhaps something entirely new. Pan-STARRS has been instrumental in discovering countless near-Earth objects, giving us crucial lead times, sometimes years, to understand their trajectories. It's a testament to human ingenuity, transforming the search from a needle in a haystack endeavor into a systematic, almost industrial process. As we've journeyed through the cosmos, exploring the incredible diversity of objects that traverse our solar system, from icy comets to rocky asteroids, a crucial question emerges. How do we find them? How do we track these fleeting cosmic visitors, often tiny and dark, against the infinite canvas of space before they make a dramatic entrance? This brings us to the tireless sentinels of the night sky, the dedicated observatories and survey systems that have utterly transformed our ability to catch these celestial wanderers in real time. Imagine, if you will, the world before modern sky surveys. It would mean Oumuamua was less like a comet or an asteroid and more like a cosmic kite, silently propelled by starlight. Scientists still intensely debate whether exotic ice theories, while challenging conventional cometary understanding, provide a more plausible, albeit unusual, explanation for Oumuamua's acceleration. Or if the light sail concept, despite its almost fantastical implications for a naturally formed object, better fits the complete lack of any visible outgassing. Each hypothesis attempts to reconcile the observed acceleration with the frustratingly absent cometary activity. What if the acceleration wasn't due to internal expulsion, but an external force acting on its very structure? As we've explored Oumuamua's initial observations, its peculiar elongated shape and tumbling motion already hinted at its unique nature. If it were not just elongated, but also incredibly flat, like a cosmic pancake or a thin sheet, perhaps only a millimeter thick, but hundreds of meters wide, then the constant bombardment of photons from the sun, a force usually negligible for larger, denser objects, could become significant. Hydrogen and nitrogen gas are incredibly difficult to detect from Earth, especially if they disperse quickly without carrying much dust. Unlike water vapor, which often brings along reflective dust grains, these lighter, more transparent gases could have simply vanished into space, providing the necessary thrust without leaving a visible signature. You might visualize a silent, invisible stream of gas propelling the object forward, a ghost in the cosmic machine. This mechanism could explain the observed acceleration without the telltale cometary signs, offering a neat solution. Researchers used sensitive spectrographs and high-resolution cameras, searching for that telltale fuzziness, the faint glow of escaping volatiles, the reflective shimmer of a dust tail. You find nothing. It appeared, to all intents and purposes, like a bare, inert rock, devoid of any cometary activity. Yet the data unequivocally showed it was accelerating. How could an object be pushed without emitting anything detectable? This was the central paradox. This striking absence of evidence for traditional outgassing ignited a vigorous scientific debate, forcing researchers to venture into more speculative territory. Scientists measured this tiny deviation with incredible precision, cementing Oumuamua's status as a profound enigma. It was speeding up, ever so slightly, but definitely, as it moved away from our star. This unexpected behavior immediately sent scientists scrambling for explanations. The first, and most obvious, suspect for any small celestial body behaving this way is outgassing. Think of a comet, that quintessential dirty snowball. As it nears the sun, its frozen water and other volatile compounds heat up, sublimating directly from solid to gas. The fact that we've observed such a range, from dense, possibly metallic, to volatile, rich, icy bodies, to fragile cometary aggregates, suggests that the processes of planet formation and the creation of smaller bodies, both rocky and icy, are not unique to our solar system. Instead, they appear to be universal phenomena, occurring with fascinating variations in star systems across the vast expanse of the cosmos. Each visitor, therefore, is not just a passing curiosity, but a precious sample, offering a glimpse into the raw materials and conditions present in other stellar nurseries, far, far away. Atlas was a testament to the delicate nature of many comets, a stark reminder that these beautiful celestial wanderers are often ephemeral, especially when they venture too close to a star. Its breakup provided a rare, real-time glimpse into the structural integrity, or lack thereof, of an icy body. reinforcing our understanding of how comets evolve and eventually meet their end. These three objects, distinct in their material makeup, collectively paint a vibrant picture of diverse cosmic chemistry. Oumuamua, potentially rocky or metallic and devoid of visible ice, challenges our preconceived notions of interstellar objects. This was the unmistakable signature of a body rich in frozen volatiles, essentially a classic comet, but from another star. Spectroscopic analysis revealed not just water ice, but also significant amounts of carbon monoxide, CO, and carbon dioxide, CO2, ice. These are particularly volatile compounds, meaning they sublimate or turn directly into gas at much colder temperatures than water. The abundance of these deep freeze volatiles suggested that Borisov originated from an incredibly cold region of its home star system, perhaps a gas giant's outer reaches, far beyond its equivalent of our own Kuiper belt. When astronomers peered at it, they found no visible signs of the fuzzy coma or tail that typically betrays the presence of ice sublimating under the sun's warmth. Instead, its surface appeared dark and reddish, much like some of the most ancient, radiation-baked asteroids in our own solar system. Observations suggested a density consistent with rocky or even metallic materials, perhaps a dense, solid object that had long since shed any superficial ice, or perhaps never had much to begin with. This lack of discernible ice was a profound puzzle, especially given its interstellar provenance. It highlights that Earth, despite its protective atmosphere and magnetic field, is not an isolated bubble, but an active participant in a cosmic dance, subject to the whims of forces far beyond our control. This awareness fuels the ongoing scientific endeavor to not only track these objects, but also to develop potential deflection technologies, ensuring we are prepared, however remote the threat. Some theories suggest our current telescopes are incredibly efficient at spotting larger objects, while others argue that smaller, darker comets or stealth interstellar objects could potentially slip through our observational net until they are much closer. The challenge isn't just seeing them, but seeing them early enough to do something about it. Compared to the risks posed by asteroids already orbiting the Sun, whose paths are generally more predictable and whose numbers are more thoroughly catalogued, the risk from truly new celestial objects is often considered even lower. For example, a planet-killer asteroid, roughly 10 kilometers across, is estimated to strike Earth only once every 100 million years on average. Smaller, but still significant impactors, say 100 meters across, capable of regional devastation, might hit every few thousand years. While these numbers sound daunting on their own, consider the constant rain of cosmic dust and tiny meteoroids that bombard our atmosphere daily. Most burn up harmlessly, a spectacular light show for those who witness it. The good news, the truly reassuring news, is that the probability of a catastrophic impact from a newly discovered large-scale object, be it a long-period comet or an interstellar visitor like those we've discussed, is incredibly, almost unimaginably low. Scientists constantly monitor the skies, cataloging near-Earth objects, or NEOs, which are asteroids and comets whose orbits bring them within 1.3 astronomical units of the Sun. This builds on sophisticated detection networks, a global effort that has identified over 30,000 such objects to date. These visitors offer us fleeting, invaluable glimpses into the diverse chemistry, geology, and dynamic processes of other stellar neighborhoods, carrying with them secrets from worlds we may never directly observe. They are silent, swift messengers, reminding us that our solar system is not an isolated island, but an open port in a bustling, interconnected galactic ocean, constantly exchanging material with its neighbors. Others, more controversially, have even speculated about an artificial origin, though this remains a fringe idea, largely unsupported by evidence. Yet it underscores the sheer strangeness of the observation. The precise origin of these interstellar visitors, which specific star system they came from, and the exact mechanism of their ejection, is a profound cosmic cold case. It's a mystery we're still actively working to unravel, waiting for more clues from future interstellar detections. When it eventually encounters another star system like our own, that star's gravity acts as a temporary guide, shaping its path into that distinctive hyperbolic curve before releasing it back into the cosmic void. It's a grand celestial relay race, with gravity as the baton pass, potentially sending these objects towards yet another star system, light years away. The mystery deepened when you considered its sheer speed upon arrival. It carried an excess velocity, a definitive fingerprint confirming it was not gravitationally tied to our sun, but rather an independent traveler from the vast interstellar medium. These objects are more than just astronomical curiosities. They are pioneers on what we can truly call hyperbolic highways. Think of them as the cosmic equivalent of intergalactic expressways, not paved with asphalt, but carved by the relentless, universal laws of gravity. Though Borisov appeared more like a traditional comet, complete with a visible coma and tail, its extreme velocity and hyperbolic path confirmed its status as a cosmic tourist, passing through our neighborhood on its way to somewhere else entirely. These weren't objects born in our solar nursery. They were cosmic travelers, briefly gracing us with their presence. What makes these visitors so profoundly unique? Oumuamua, in particular, presented a series of quirky, lesser-known details that baffled and intrigued astronomers from around the globe. It wasn't a fuzzy comet with a glowing tail, nor a spherical asteroid. It's like throwing a ball so hard it leaves Earth's gravity entirely, never to return, except on a cosmic scale, powered by the initial ejection from a distant star system. The gravitational interaction is a brief, intense encounter, a cosmic slingshot that redirects the object but doesn't imprison it. The astronomical world collectively held its breath in 2017 when the first confirmed interstellar object, designated Oumuamua, was detected by the Pan-STARRS telescope in Hawaii. Its name, Hawaiian for scout or messenger from afar, perfectly encapsulates its role as a trailblazer. As we've explored the elegant dance of planets and comets, forever bound in the sun's gravitational embrace, you might imagine our solar system as a closed cosmic ballroom, where every participant follows a predictable, repeating rhythm. But occasionally, a stranger waltzes in, moving with such audacious speed, such an independent spirit, that it simply refuses to stay. These are the interstellar visitors, and their paths are not the familiar ellipses we've come to know, but something far more liberating and boundless, hyperbolic trajectories. Imagine yourself as a cosmic traffic controller, witnessing a celestial traveler approach your star system. Or conversely, was it an older, tired comet, its structure already compromised by previous, unobserved, close encounters with the Sun or other massive bodies, making its final demise almost inevitable? Some theories suggest that the rate of heating, not just the absolute temperature, plays a crucial role. Others argue that the presence of specific, highly volatile compounds deep within the nucleus can act as internal pressure bombs. This event, while disappointing for observers hoping for a celestial spectacle, provided invaluable real-time data. The dozens of fragments, each a ghostly echo of the once promising nucleus, continued along a similar trajectory for a time, a procession of cosmic ghosts, their collective brilliance fading rapidly. No longer a single coherent object reflecting sunlight, they dispersed, their individual surfaces too small, outgassing too weak, eventually becoming too faint and diffuse, merging back into the background of space. And here lies an enduring academic tension that continues to fuel research. While the general mechanisms of solar heating and tidal forces are well understood, scientists still debate the precise tipping point for cometary fragmentation. It stretches and squeezes the comet, much like our moon's gravity creates tides in Earth's oceans. But here, the ocean is the comet's very structure. This stretching and squeezing, acting in concert with internal pressures from outgassing, was enough to wrench apart the loosely aggregated material of the comet's nucleus, pulling it limb from limb until it fractured. The result was a celestial tragedy, a comet literally falling apart at the seams. Its journey ending not with a bang, but with a series of quiet yet dramatic breaks. As Atlas drew closer to the Sun, the increasing solar radiation began to heat its icy surface with an intensity it had never experienced before. Certainly not in the frigid outer reaches of the solar system, where it spent millennia. This wasn't just gentle sublimation. This was a rapid, violent process, causing immense pressure to build within the comet's interior. Subsurface pockets of highly volatile ices, like frozen carbon monoxide or carbon dioxide, could have suddenly vaporized, creating miniature explosions that literally blew chunks off the nucleus. But then, by spring 2020, the dream shattered. The initial excitement, the burgeoning hopes for a great comet, collapsed into a profound disappointment that echoed across the scientific community and eager observers. Telescopes, once focused on charting its glorious ascent, now capture the far more somber spectacle. Comet Atlas was disintegrating. What began as a single promising nucleus, a dirty snowball hurtling through space, fragmented into dozens of distinct pieces, each now a smaller, fading echo of its former self. As we've journeyed through the icy depths and fiery approaches of comets, we've seen the incredible promise they hold. A chance to glimpse the primordial past, a potential for breathtaking celestial displays. And perhaps no comet in recent memory captured the public imagination quite like C2019 Y4, better known as Comet Atlas. For a brief, shining moment in early 2020, Atlas promised to be a showstopper, a truly spectacular naked-eye comet, potentially rivaling Venus in our night sky. Astronomers and skygazers held their breath, tracking its inbound journey with rigor and hopeful anticipation. The truth is likely a complex interplay of several factors, a cosmic recipe for destruction. The story of Comet Atlas, the comet that promised so much and then dramatically broke apart, serves as a powerful testament to the unpredictable, dynamic nature of our solar system. It reminds us that even when we think we understand the patterns, the universe always has a new twist, a fresh mystery, an unexpected display of its raw, untamed power. The fragmentation of Comet Atlas offered scientists an unprecedented opportunity to study such an event in detail. As we saw earlier with the interstellar objects, understanding these celestial bodies helps us piece together the solar system's history. But with Atlas, it was about understanding the present-day dynamics of a comet on its death throes. Each fragment, though tiny, provided a new surface for sublimation, briefly flaring before dissipating. It was a fleeting, multifaceted farewell. What began as a single, promising nucleus soon fractured into multiple pieces, then dozens, perhaps even hundreds, of smaller fragments. Imagine a colossal, dirty snowball, slowly disintegrating under unseen forces, its constituent parts scattering across space, each piece briefly catching the sunlight before fading into oblivion. This wasn't the spectacular display of a unified, brilliant comet. It was the poignant, gradual demise of one. This disintegration was a stark reminder of the fragile nature of these cosmic wanderers. Comets are not solid, immutable rocks. They are loosely packed agglomerations of ice, dust, and rock, often described as dirty snowballs. The kind that graces our skies with a dazzling tail, visible even in daylight. A celestial spectacle that captivates generations. For a brief, thrilling period, it seemed entirely possible. Models predicted it would become a naked-eye object, potentially as bright as Venus, a radiant beacon in the dawn sky. Imagine the anticipation. Stargazers preparing their telescopes, photographers scouting dark sky locations, children dreaming of a cosmic light show. This comet was behaving like a true showstopper, its coma expanding, its tail beginning to stretch. As we've journeyed through the mysteries of interstellar visitors like Oumuamua and Borisov, objects that traversed the vast cosmic ocean to briefly grace our solar system, our gaze now turns to a different kind of wanderer. One with a more familiar, yet equally dramatic origin story. In late 2019, astronomers turned their eyes to a comet that was, in essence, homegrown, Comet Atlas, officially designated C2019 Y4. Unlike its interstellar predecessors, Atlas likely hailed from the Oort cloud, that distant icy shell enveloping our solar system, a vast reservoir of primordial material. Some theories suggest that variations in the stellar nurseries where these comets originate, perhaps differences in the initial cloud's density, temperature, the metallicity, abundance of elements heavier than hydrogen and helium, or the proximity to other massive stars, could lead to distinct chemical fingerprints, subtle variations in these ratios that could tell a unique story of Borisov's birth. Others argue that the fundamental physical and chemical processes of planetary and cometary formation are so remarkably universal across the galaxy that such variations might be minimal, leading to largely interchangeable cosmic building blocks, regardless of their stellar parent. While the general overarching composition of Borisov mirrored our own comets, providing a broad brushstroke of familiarity, scientists are still meticulously investigating whether the precise ratios of these complex organic molecules or the subtle but crucial isotopic signatures within the water ice and other volatiles might subtly differ. For instance, the ratio of deuterium to hydrogen, DH, in water ice can act as a cosmic thermometer and a tracer of origin, revealing the temperature and environment where that water originally formed. It hinted that the fundamental processes of star and planet formation, the types of ingredients available in the vast stellar nurseries across the galaxy, might be far more uniform and predictable than we once dared to imagine. It implied that the raw materials for life, the very same ones that seeded our own planet, might be ubiquitous throughout the cosmos. This gave a powerful boost to the idea of cosmic universality, suggesting that if life arose here, it could potentially arise in countless other places where similar conditions and materials exist. The spectral signatures clearly revealed the copious presence of water, the very essence of life as we know it, alongside carbon monoxide, a common simple molecule abundant in cold, dense molecular clouds, the stellar nurseries where stars and planets are born. But perhaps most captivating, and certainly most intriguing for astrobiologists, was the detection of various complex organic molecules. These aren't necessarily life itself. They are the carbon-based building blocks, the molecular Legos from which life can assemble if you were simply observing it through a telescope. Unaware of its incredible interstellar journey, you might easily mistake it for one of our own solar system's homegrown icy wanderers, a classic dirty snowball comet born right here in our cosmic neighborhood. This visual transformation from an inert rock to a dazzling celestial beacon was the first powerful hint of its surprising normalcy. But the true marvel, the deeper connection that resonated through the scientific community, came when scientists turned their most sophisticated spectroscopic instruments towards this cosmic guest. The frozen ice is on its surface, a mixture of water, carbon monoxide, and other volatile compounds, shielded for millennia in the frigid depths of space, started to sublimate, transforming directly from solid to gas without first becoming liquid. This process, known as outgassing, is the defining characteristic of a comet. As these gases escaped, they carried with them tiny grains of dust, forming a bright, hazy envelope around the comet's solid nucleus. what astronomers call a coma. This coma, often hundreds of thousands of kilometers across, can outshine the nucleus itself. It was a chance to touch, metaphorically, a fresh piece of another star system, to hold it up to the light and see what secrets it held about the broader universe, about the commonality or uniqueness of our own cosmic backyard. And it all began with one person, one homemade telescope, and a persistent, curious gaze into the night sky, reminding us that sometimes the most profound discoveries emerge from the most unexpected places. Some theories propose that such normal comets are far more common than Oumuamua-like anomalies, simply because their outgassing activity makes them brighter and therefore easier to detect from vast distances. Their tails act like cosmic signposts, drawing our attention. Others argue that Oumuamua's bizarre, inert nature might be more representative of the truly ancient, processed material that has survived long, destructive journeys through the galactic void, stripped of its volatiles, while Borisov might represent a younger, less altered ejecta, perhaps only recently kicked out of its home system. For the first time, scientists had a comparative case study. They could analyze an interstellar object that looked, felt, and acted remarkably like the comets born in our own solar system's distant Oort cloud. This offered an immediate, tangible glimpse into the composition of another star system's building blocks. Spectral analysis using instruments like the Hubble Space Telescope and the Atacama Large Millimeter Submillimeter Array, ALMA, quickly revealed a chemical signature rich in familiar molecules. Water, carbon monoxide, hydrogen cyanide, and even diatomic carbon were detected, all in proportions surprisingly similar to those found in our own solar system's comets. It was the second such object ever definitively identified, a momentous discovery that doubled our direct evidence of cosmic wanderers from beyond our solar neighborhood. But here's where Borisov diverged dramatically from its predecessor. While Oumuamua baffled scientists with its lack of a cometary tail and its peculiar elongated cigar-like or pancake-like shape, 2I Borisov behaved exactly as a textbook comet should. As it drew closer to our sun, the increasing solar radiation warmed its icy nucleus. You can picture it, a cosmic snow globe, perhaps a few kilometers wide, beginning to melt under a foreign star. In the quiet solitude of his backyard near the city of Nauchny, Crimea, an amateur astronomer named Gennady Borisov was doing what he loved most, sweeping the heavens with a telescope he had built himself. This wasn't some off-the-shelf device. It was a testament to personal dedication, a meticulously crafted instrument with a 65-centimeter mirror, painstakingly ground and polished. Through its lens, he spotted a faint, fuzzy smudge of light, a new comet steadily tracing its path across the backdrop of distant stars. It was a discovery born of patience, skill, and an enduring passion for the night sky. Its defiance of conventional categories forced astronomers to reevaluate their understanding of what objects populate the interstellar medium, pushing the boundaries of what we thought possible. It was, in essence, a cosmic enigma, a needle in the dark, challenging every established notion about how these celestial nomads behave, and what they're made of, opening a whole new realm of astrophysical inquiry. Indeed, the physics governing its motion and rotation hinted at something profoundly different, challenging fundamental assumptions about how celestial bodies form and evolve. It was a true outlier, a rogue object that shattered established taxonomies. Scientists still debate whether Oumuamua represents a new class of interstellar object, perhaps a fragment of a shattered exoplanet, a remnant of a star system's formation violently ejected, or even something more exotic. Observations revealed a deep reddish hue, a color often associated with objects baked by eons of exposure to harsh cosmic radiation, a process known as space weathering. This cosmic ray-weathered surface suggested a robust composition, perhaps rich in complex organic compounds or metallic silicates, rather than pristine, volatile-rich ice. It was a testament to its unimaginably long journey through the galaxy, a surface aged and transformed by the brutal, energetic environment of interstellar space, a cosmic tan earned over millennia. You might naturally expect an object journeying from the frigid, deep-freeze depths of interstellar space to be rich in volatile ices. As it approached our sun's warmth, these ices should have vaporized, creating a magnificent glowing tail and a fuzzy envelope of gas and dust, a cometary coma. This is the classic signature of a comet, our solar system's icy wanderers. Yet, Oumuamua remained stubbornly silent. No visible gases, no telltale dust cloud, no glorious tail, even as it passed closer to the sun than Mercury. It behaved not like a comet, but like a bare, inert, dry rock. It was as if a cosmic top had been flung into existence, tumbling in all directions, refusing to find a steady rhythm. From these extreme, baffling light curves, scientists deduced a shape that defied all expectations for a naturally occurring object. This wasn't a neat sphere, nor even a slightly elongated potato like most asteroids we know. Instead, the data pointed unequivocally to an object with incredibly extreme dimensions, either a cosmic needle, perhaps 10 times longer than it was wide, or an impossibly flat, thin pancake, many times wider than it was thick. As we saw earlier, Oumuamua's presence was groundbreaking, the first confirmed visitor from beyond our sun's domain. But as it began its rapid exit, leaving our cosmic neighborhood behind, the torrent of data it transmitted back to Earth started to reveal an even more profound and perplexing mystery. Imagine trying to sketch the precise, three-dimensional form of a distant, tumbling object by simply observing how its reflected sunlight brightens and dims. This intricate light curve analysis, performed by astronomers, yielded astonishing results, challenging decades of celestial understanding. What they observed wasn't a steady, rhythmic pulse or a gentle, predictable wobble. It compels us to ponder the prevalence of such wanderers and what they might tell us about the building blocks of life itself, scattered across the interstellar medium. This encounter with Oumuamua wasn't just about identifying an object. It was about opening a new frontier. It proved that interstellar visitors are real, and that our telescopes are now capable of detecting them. Some theories suggest it might have been a dark comet with an unusual composition, while others argue for a more exotic explanation, including the highly speculative yet captivating idea that it could be an artificial object, a technological artifact from an alien civilization. While the scientific consensus leans heavily towards natural phenomena, the sheer uniqueness of Oumuamua keeps all possibilities, however remote, alive in the minds of researchers and the public alike. The implications of Oumuamua's visit are staggering. Telescopes worldwide scrambled to observe this unprecedented guest before it vanished back into the interstellar void. But Oumuamua proved to be a mysterious and elusive subject. Its light curve suggested an incredibly elongated shape, unlike anything we had ever seen in our solar system, often described as being like a cosmic cigar or a space cucumber, perhaps 10 times longer than it was wide. This bizarre, tumbling form was a quirky detail that immediately set it apart, sparking endless speculation about its formation. As Oumuamua sped away, another perplexing characteristic emerged. Scientists detected a slight, continuous non-gravitational acceleration. Initially, it seemed like just another asteroid, a calming find in our bustling solar system. But then, astronomer Robert Warwick, reviewing the data, noticed something peculiar. This object's trajectory wasn't the familiar elliptical path of something gravitationally bound to our sun. No, its orbit was decidedly hyperbolic, a trajectory that meant it was moving too quickly to be captured by the sun's gravity. It wasn't orbiting our star. It was merely passing through, a transient visitor from the vast, dark expanse between star systems. This was it, humanity's first confirmed interstellar object, a true wanderer from another star, designated One-Eye Oumuamua. Their arrival fundamentally expands our cosmic perspective, inviting us to ponder not just what falls from our own skies, but what might be passing through from the infinite expanse of the galaxy, carrying clues about other worlds, other suns, and perhaps even other forms of life. Some scientists have even proposed, controversially, that its unusual characteristics, its extreme shape, lack of coma, and non-gravitational acceleration might hint at an artificial origin, a relic of an advanced civilization. However, the vast majority of the scientific community leans towards natural explanations involving unusual ice compositions or unique formation processes in other star systems. Acknowledging the immense statistical likelihood of natural phenomena over artificial ones, this academic tension underscores just how unique and challenging these interstellar visitors are to categorize and understand, pushing the boundaries of our existing models. Their trajectories are the definitive giveaway. Instead of orbiting the sun like everything else in our solar system, they follow distinct hyperbolic paths. This means they approach our sun with such high velocity that its gravity isn't strong enough to capture them into an orbit. Instead, they slingshot around our star and then depart, accelerating back into interstellar space, never to return. This distinct, open-ended trajectory is the unmistakable signature of an object originating from outside our gravitational sphere of influence, a cosmic fingerprint of its extrasolar birth. The scientific community was, and remains, captivated by these interstellar interlopers. Oumuamua, in particular, presented a fascinating puzzle. Beyond its unusual, highly elongated or flattened shape, it exhibited a slight, inexplicable, non-gravitational acceleration as it sped away from the sun, as if something was subtly pushing it. This behavior is typical of comets outgassing, but Oumuamua showed no visible tail or coma, defying easy explanation. Consider the sheer scale and implications. Oumuamua, a name meaning scout or messenger in Hawaiian, was estimated to be hundreds of meters long, an elongated, cigar-like shape, or perhaps a flat pancake, depending on the viewing angle, far larger and more substantial than any typical dust grain meteor. Borisov, on the other hand, was a comet several kilometers in diameter, complete with a tail of gas and dust, a truly massive object by comparison to our everyday shooting stars. Yet, while these common celestial fireworks are familiar, our skies have recently hosted a far rarer, more profound class of visitor. Objects that originate not from our own solar system, but from beyond. This discovery fundamentally altered our cosmic perspective. In 2017, astronomers using the Pan-STARRS telescope in Hawaii detected Oumuamua, the first confirmed interstellar object to pass through our solar system. Its discovery was a monumental event, confirming a long-held theoretical prediction that such objects must exist. The immense kinetic energy of these fast-moving particles is rapidly converted into heat due to friction with atmospheric gases. This intense heat causes the dust to incandesce, creating that brilliant, momentary flash you see. It's a spectacular, yet ultimately harmless, atmospheric phenomenon, occurring tens of miles above your head. For millennia, these fleeting streaks of light have inspired awe, superstition, and even the hopeful tradition of wishing upon a shooting star. A beautiful irony, as you're actually wishing upon a grain of cosmic dust meeting its fiery, incandescent end high above. As we journey through the cosmos, you might imagine our planet as a cosmic catcher's mitt, constantly bombarded by celestial debris. But what exactly are these falling objects? And do they all count the same? The answer, as you'll discover, is a profound no. Our understanding of what crosses Earth's path has dramatically expanded, revealing a universe far more interconnected and dynamic than previously conceived. For most of human history, when you looked up and saw a fleeting streak of light, you were witnessing a meteor, often romantically called a shooting star. Imagine standing under the vast, inky canvas of night, a silent witness to the cosmos. In just a few short years, 3 utterly distinct cosmic wanderers sailed through our solar system. First, the enigmatic Oumuamua, then the pristine comet Borisov, and finally, the mysterious near-interstellar object Atlas. Each was a silent, fleeting visitor, carrying tales from star systems light years away, yet all arrived under the very same sky we gaze upon. Scientists still debate the precise origins and true nature of these interstellar guests, whether they are mere cosmic debris, rogue comets, or something far more exotic.